Hello, my name is Edward White. I'm an FSU math PhD student, and I'm in my sixth year, expecting to graduate pretty soon. And I want to thank the organizers for letting me talk to you about asymptotics of best packings and best coverings. So this is some work that we had that was recently published, and I want to tell you about some of the a little bit of results that we were able to work through. So I want to start out by just giving you a brief overview of the problem, which is that we have these two main concerns. Given a compact set, what is the maximal number of closed disks that can be packed into that set? And then similarly, we have what could be thought of as the dual problem, which is what are the minimal number of closed disks needed to cover a given compact set? And then related to this, we could think about how this could be applied in some other settings, such as if you give me a type of gas and it needs to fit into a large container, how is that gas going to expand to fit that container? Or how would you distribute an important resource to cover a given large area that maybe has an irregular shape? So to give you an example that sort of gives you a visual idea of what we're talking about, I have two contrasting examples, both of a square where I have four disks covering that square. Now I have on the left what we would consider an optimal covering. So we can see that by spacing my disks appropriately, I can keep the radius of the four disks relatively small, such that I am as optimally as I can covering the area of the square without having too much overlap that we could consider as wasted space. Now, over here on the right, what I've done is I've taken the four centers of these optimal disks and pushed them closer to the center of the square. Now, what that does is it makes these four centers of those disks farther away from these corners of the square, which necessarily means that I have to increase the radius of those covering disks in order to ensure that I'm still covering the entire square. So this would be an inefficient covering because I require a larger radius in order for my disks to cover the full square. Whereas if I place my configuration of the centers of the disks appropriately, I can get a more efficient or optimal covering. So this is one example to contrast what we consider optimal versus non-optimal. Now let's get into the details of some of the definitions. So for the remainder of this talk, our ambient space will be RP, and we'll always consider a configuration that we'll call omega n for brevity, which will just be a collection of n points, which we're just taking inside that ambient space. Now, first, we want to consider what we'll call best packings, where we'll look at the minimum pairwise distance between any pair of points of this endpoint configuration. So we'll just run through all those endpoints and find what's the minimal distance between any pair, and that will be our packing distance delta of omega n. All right, so then if you hand me a compact set A, and it's important that we want to consider an infinite set A, so not a discrete like set of points, but an infinite set, so something with infinitely many points, we can take a look at that packing over that set A by n points by looking at the supremum of all packings of omega n. So we take our in collection of points, we stuff them all into A, and we just check, okay, let's find the minimum pairwise distance. And now we want to run a supremum so we can see how far can we push away those points. So here we have another example to sort of illustrate this point. So down here, I have a closed unit interval from 0 to 1, and this will be my set A over which I'm packing. And for these two examples, we'll take our n points to be 5. So we're packing 5 points into this unit interval. And I want to pack them as well as I can to give as much separation between the points. So over here on the left, we see that the optimal choice is to start by putting 2 endpoints or 2 of our collection points at the endpoints, so at 0 and 1. And then that leaves the interior. So we have to put the remaining 3 points in the interior and equally space them as much as possible. And we see that this is pretty well separated because that separation distance is the same between any of the 2 nearest points. Over here on the right, we have another suboptimal example where we can see that I've clustered too many of these points together, and I have all this free space to the left and all this free space to the right. So we can visually see how this is suboptimal because I've sort of casually placed all these points near to each other, but I've left all this room that I could slide, say, this point all to the left and then increase my optimal packing. Now, to contrast that, we have what we can call the best covering, which will be just a slight variation, and I'll justify the use of that word dual earlier by looking at how this is defined. So again, we'll take A to be an infinite compact set, and we'll define what's called the best constrained covering distance of endpoints of A as the following. So we'll take our configuration omega n, and then we'll look at points y taken inside of our infinite set A, and look at the distance from y to all the points of omega n. And we'll find what is the farthest point in A away from all of my configuration points omega n. So what's the farthest point away from my configuration? And then we'll run a minimum argument where we want to move those points in the configuration around such that we are minimizing that distance. So we were trying to move our configuration points to be as close to all the distant points in A as much as possible. So we can look back at the first example. So here in the inefficient covering, I had the centers of the disk being my configuration points. So omega 1, or I guess y1, y2, y3, y4 to make omega 4. And we see that the distant points of A are the corners of the square. These are the points that are farthest away from all the configuration points. And by moving the points of my configuration closer to those corners, those distant points y in A, I get a more optimal covering. So that's the argument of how this optimal covering is working. And we'll notice in particular also the ordering of the arguments has sort of switched around. We start by taking a max and then we take a min. And that's sort of the reverse of the packing, which was we started with a min and then we took a sup. So if we think sup and max acting sort of in a similar way, and then min and inf acting in a similar way. All right, and then we have what we can also call the unconstrained covering, where instead of restricting our configuration points covering the interior of A, we can say, let's just in general let our covering points be anything in the ambient space and call this the unconstrained covering. So this would be important for the case if our set A is not necessarily convex. So we'll note that A, we want to be infinite and compact, but not necessarily convex. So in the trivial case where A is convex, then these two things are essentially the same. But if A is non-convex, then we in general want to consider the unconstrained covering. All right, and then what the common thread is that ties all this together is what we'll get into now, which is the harmonic analysis part, which is being the minimal energy. So given a lower semi-continuous kernel, K of x, y, taking points x in A and y in A, and then it takes it from that product and sends it to minus infinity to infinity inclusive. And given a configuration omega n, given as seen previously, we can call its K energy given as the following. So we just run a summation over all distinct points xi, xj taken from that configuration. So usually in the context of what we're looking at, this semi-continuous kernel would be like the inverse distance. So 1 over the distance from xi to xj, or we could scale it so that it's 1 over the inverse of distance squared, or 1 over the inverse of distance cubed, or anything such like that. So we're looking at, for example, the sum of the inverse distances of xi and xj. And we'll call that ek of omega n. And then if we try to minimize this energy, so taking the minimum over all such configurations constrained to A, we'll call that script E of AN, the minimal K energy over all such configurations. Now, this is described by the problem of maximal polarization, which is to take that same semi-continuous kernel and look at the pairwise distance from some fixed point y to all your points omega n, and then consider the minimum over all points y in A of that summation of those kernels. Then the nth kth polarization, or sometimes called the Chebyshev constant of A, is defined as that supremum of pk. So again, a lot of notation, but I just want to in particular focus on, we had this argument, and then we took an infimum over it, and then we took a supremum over it. So first an inf, then a sup, and that matches, in a vague sense, taking the minimum and then taking a supremum. So that sort of wrapped argument of we had this polarization and then we took an infimum and supremum, in fact, exhibits the type of behavior that we see for a best packing, which is that if points are too close, you're sort of inefficient. So what we want to do is try and space the points as far away as possible and spread them out across the constrained set of A. And so that's the common thread that ties these two together, is that polarization is the sort of harmonic analysis way of understanding packings and then its dual related covering problem. So what's the goal is we want to take our optimal polarization and we want to take some known results from this area and hopefully extend them to coverings and packings. Then we want to take coverings and packings and try and push that into a new direction to get some new results, hopefully for coverings and packings, and then hope that because of the relation between polarization and then coverings and packings, that this would lead us back to polarization to get some new results under polarization. So this gets into sort of the main theorem that I want to talk about, which is this following theorem here. And I just want to start by giving the key motivation. So the motivation is to study the asymptotics of these packings and coverings as a limiting argument. And as a point that I'll get into later, it turns out that it's a little bit easier to understand the asymptotic behavior if we let the number of points in our configuration grow towards infinity to get an understanding of the general behavior as opposed to looking for exact optimal solutions for fixed n. So here's a layman's description or somewhat layman's description of our theorem. So given a reasonably nice, and I'll wait till the end of the talk to give a slightly more descriptive answer for what reasonably nice means, compact set A living in our ambient space RP, and then for integers D and P, so P being the integer describing our ambient space dimension, and D, which I'll get into in a little bit, satisfying the following. So D and P both need to be at least 1, P needs to be at least 2, and D cannot be bigger than P. Then what we have is this limit, so taking the number of points and sending it to infinity of our unconstrained covering of endpoints on A, and then multiplying it by this growth factor into the 1 over D power. If this limit exists, then this implies the limit of the constrained covering multiplied by n to that 1 over D. So again, that same growth order constant, or that growth order, that these limits will exist and they also agree. So the implication is that if we know something about the unconstrained covering, then that implies something about the constrained covering, and that moreover, that these will agree under a limit as we approach infinitely many points. So this result and its contrapositive has additional results that I'll be discussing later on, but for the sake of time, we'll only look at sort of the main result that I really want to talk about today. So why are we talking about asymptotics? It's because proving exact answers is in general very hard. And to give a brief overview of this, you can look into something called the Thompson problem, which looks at best packing or equivalently best covering of endpoints on the unit sphere. And we know that for only a few instances, it's been proven what the exact solution is, but that otherwise there's a lot of conjectured answers. So proving them in the exact sense is in fact very hard, and has been a known hard problem for a long time, which is why we want to consider what happens if we let this grow asymptotically and understand the asymptotic behavior. So from the previous slide on the theorem, D is representing our Hausdorff dimension of that set A. So if A is contained in our ambient space RP, then certainly it makes sense why D couldn't be bigger than P, because our Hausdorff dimension of A can't be larger than its ambient space containing it. Now, earlier we had that growth order, and this is justified by this following description here, which is that the best packing of A, the best covering of A, and the best unconstrained covering of A all have that same growth order of n to the minus 1 over D. So again, this is just further justification for why we group these all together as sort of acting in a similar or at least dual sense, is that they all have this same growth type behavior of n to the minus 1 over D as we let n grow to infinity. Now let's just consider the simplest case in order to get an intuition as to why this is true. Let's consider an line segment from 0 to some number L. So it'll have a length L. Then the best constrained covering of our set A, where A is that segment 0 to L of n points, will be, okay, so if our n is 5 in this case, we'll just cover it by placing 5 points equally spaced in such a way that we're covering from the left endpoint to the right endpoint. So we can do this by just having the disks be tangential to each other and having essentially no overlap. So by doing it this way, we can see that the covering radius of the disks will be, so if we took 5 disks to cover length L, then the radius will be half of the number of disks needed. So 1/2 of 1/5 of the total distance will be over 10. So the total length L divided by 10, which is described here by L over 2m. So this is on that growth order of n to the minus 1 over our Hausdorff dimension of this line segment is 1. So minus 1 over 1 is just n to the minus 1, which explains why we have an n in the denominator and not n squared or n cubed. So this is the simplest case of why this is true. And in general, this is still true for more general cases, but we won't really try to describe those with pictures. So this gets into one of the main results in this area, which are called the aptly named Poppy Seed Bagel Theorem, and we'll see why this is such a great name. So under some smoothness assumptions on our compact set A, we can get the existence of the asymptotics for the best packing and the best covering, or if we extend it further to the minimal energy or the maximal polarization, et cetera, et cetera. So the theorem, the Poppy Seed Bagel Theorem, stated in terms of packing, says that let A be a smooth D manifold embedded in our ambient space, and let HD denote the D-dimensional Hausdorff measure, which for us will just be the surface measure of that manifold A. So then the limit of the best packing multiplied by that growth order into the 1 over D, because we're trying to cancel the fact that it's shrinking, will be equal to some constant depending only on that Hausdorff dimension, so C depending on D, multiplied by our surface measure of that manifold A, and then we just have to normalize it 1 over D. So in particular, we just want to note that this has the following implication, is that if you hand me a smooth manifold, so let's say it's a torus, then we can evenly and asymptotically spread a very large number of poppy seeds. So if we imagine the seeds are our covering points or our packing points here, we can evenly spread them respective to the surface measure of that torus. So we can evenly spread our poppy seeds all across the surface of our bagel and get the perfect poppy seed bagel. So we have that with this following picture where the red dots are representing those poppy seeds, where we've evenly spread them as much as possible all over the smooth surface of our manifold or all over the smooth bagel. So here I'll just quickly note that CD in this case is a rescaling dependent on the D-dimensional volume of the unit ball in RD, and then delta of D is the largest sphere packing density in RD. So this is just a quick example explaining with a visual image what that best packing looks like for some type of smooth manifold. Okay, so a version of the Poppy Seed Bagel Theorem had actually been proven by Kolmogorov and Tikhomirov, but only in the case of Jordan measurable sets and only in the unconstrained case and for full dimension with nothing about the distribution. So the distribution that we get was that we stated that the distribution should be roughly equal relative to that surface measure of whatever manifold we're considering. So Kolmogorov and Tikhomirov had a lot of constraints with their proof where they're only able to show it for Jordan measurable sets, only for the unconstrained case, only for full dimension, and nothing about the distribution of those points. So a very limited theorem, but still there was a sort of earlier example of what this type of theorem would say about these asymptotics. So what we were able to do was take that previous theorem and show that since the existence of unconstrained coverings of asymptotics implies the existence of constrained covering asymptotics, and moreover that those limits agree, we get for free the following theorem, which says that let A just be a compact set, and then following the previous lemma or previous theorem that we need that boundary measure to be 0. So essentially we need some mild smoothness assumptions. Then we just get for free that the constrained covering will match that previous limit that they obtained. So what we've shown is that the Poppy Seed Bagel Theorem for packing can be known under some very mild smoothness assumptions. And in fact, we can extend it even more. So for example, here, the mild smoothness assumptions being that the sets are the image of some compact set under a Lipschitz map. So this gets back to that description of what did I mean when I said reasonably nice? Well, here's just a slight description of that where it's the image of a compact set under a Lipschitz map. And in fact, we can relax this mild smoothness assumption even more, but that goes a bit beyond what I wanted to discuss for today and mostly just talk about sort of the initial results we were able to obtain. And that does it for my talk. These are some of the sources. And then in particular, I want to focus on the main result in which we talk about this, which is our recent publication in Advances in Math. So if you want to go read more about these details, please go check this out. I want to thank the organizers again for allowing me to speak on this, and I hope that you continue to read more about this stuff. Thanks again.